Any questions about the lecture? So this lecture was quite difficult. Yeah, this time as well. So yeah, I just wanted to briefly discuss the measure that was introduced in the paper. So let's discuss how this B cubed evaluation metric works. So in this case, yeah, the color is the correct label, and the circle or this kind of group is those found by our clustering algorithm or by any kind of linking thing. And so here, this B cubed metric is computed as follows. So we consider each of our data points and consider its or compute its precision and recall with respect to its its associated group, defined by our algorithm. So in this case, you guys understand from the perspective of this guy, the precision is computed as like 4/5, right? So far it's clear. And then in terms of a recall, it's 6/4, right? But what about this guy? So can we compute the precision and recall for this guy? Because this guy is the same, has the same label, and also it belongs to the same cluster, predicted cluster, and then it will share, or it will have the exact same value of the precision and recall. But what about this guy? Can we compute the precision and recall for this guy? Because this guy's ground truth label is this pink one, and so so let's think of the precision. And the precision is, instead of this 4/5, is 1/5 is corresponding precision, right? And then what about the recall? Recall is also 1/5, because the recall is computed from this, right? So we can compute the precision and recall for each individual data item that we have, right? And then we basically compute the average precision and recall separately for precision and the recall. So for all the precision values, so for example, for this guy, we have this precision, and then we have 4 points, right? So we compute or multiply it by 4. And then for this guy, we have a precision of 1/5. But what about this guy? This guy has the recall of 1, 2, 3, 4, 5, 6, as 4/6, right? And then we have 4 different items, right? And so we basically compute the average precision value for each individual data item. And then also we compute the recall in the same manner. And then by using this recall and precision, we can compute the F1 measure by using the same formula that we have. So this is this is the measure called this B cubed. And then so do you guys know how to compute this RAND index? RAND index. RAND index. So it's not like a random index. It has a special, kind of way of computing this measure. And so let's think of this confusion matrix. So we can basically compute all these measures after constructing our confusion matrix. So this is a ground truth cluster 1, GT2, GT3, and maybe predicted cluster 1, 2, 3, 4. So it is even possible because we cannot assume that the true number of clusters in our ground truth label, right? So it can be smaller or larger in terms of the number of clusters, but this part is a predicted one, this part is a ground truth one, okay? And then okay, so before talking about the RAND index and other measures, so let's think of this just typical accuracy measure. Accuracy. How do we compute the clustering in the accuracy? So yeah, let's just simplify this 3 by 3 case of like 1, 2, 3, 5, 6, 4, maybe 4, 3, 2. So suppose this is our confusion matrix, which means, or which indicates the count that has the ground truth label as 1 and then predicted as the second cluster. Okay. So in this case, yeah. So if it was just a multi-class classification, how do we compute the accuracy measure? The accuracy measure is the sum of these entries, right? Because it is like yeah, having a ground truth label as 1, and then it was predicted as the first class, right? And then the second one and the third one predicted correctly, and then it's like 1 plus 6 plus 2, and then the total sum of all these elements, right? So that is the accuracy, right? But when computing this accuracy in the case of clustering, yeah, we have to do one additional step before computing this accuracy, because in this case, let's see, we do not know the matching between these cluster labels and the ground truth labels. So because we don't, this is not a supervised learning, it's just about the kind of pure grouping, regardless of like, yeah, I mean, rather than like correctly grouping the first group as really the first, like the group that has the particular meaning in our ground truth label, right? So yeah, this may be matching with this guy, and this may be matching with this and this and this, right? So we have to do this kind of matching process first, and then there are many different matching process, but one really widely used kind of greedy style of a matching process is called the Hungarian algorithm. Yeah, so let me just quickly describe Hungarian algorithm. So in this case, we just look for, I mean, let's just try to maximize our accuracy. And then in this case, so let me just change it as 6 and maybe 3. So in this case, the greedy strategy that we can do is to pick up the largest entry among these 3 by 3 grids, or all these possible kind of cases. So in this case, yeah, we can infer that this guy is matching the predicted class 3, right? And then we can just treat these as kind of false negative or false positives, which are incorrectly classified, right? For the first one, with the ground truth label, and then it was misclassified with the other two, and these are kind of precision related things, right? It was predicted as the third group, but it was actually having the different ground truth label. But yeah, so in that sense, all these red ones are considered as inaccurate or misclassified one. And then what are the remaining entries? The remaining entries are these 4, right? So in this case, yeah, so we basically remove this row and column from our matrix by picking up the largest entry, and then in this remaining ones, we just look for the largest one, and then it will be this one, right? And then we consider this one is matching the first one, and then we also remove this guy and then this guy. And so our accuracy is like 653 and the total divided by the total sum, right? So this is how we compute this accuracy in the clustering kind of thing. And then also in practice we can do this by reordering rows and columns. So if we fix the rows and then if we reorder the columns, and then we can think of it as like moving this column into the first column, and then this guy as the second column, and then the remaining one as the third one. Okay, so in this case, where is these six? Where are these 6, 5, and 6, 5, and 3 are placed? So we have 6, 5, 3 are placed along the diagonal entries, right? So this is like a proper confusion matrix after this alignment step, which is done by this Hungarian algorithm. Okay, then so this is the typical accuracy measure. And then let me see. Let's think of a general case and then move on to the rand index thing. So the rand index thing is this guy. So suppose we have maybe 10 different entries, maybe 1, 2, 3, 4, 5, 6. And then let's just remove because so that we can use just a simpler case. And then the total sum will be 21. Okay, so in this case, let's just imagine all the possible cases of picking up a pair of items from these 21 different examples. And then these ones are the total ones that we have, right? And in this case, among all these possible cases, we basically consider the number of properly clustered one. So this is still a ground truth 1 and 2 and predicted 1 and 2 and 3. And then so what are those numbers? So in order to consider the properly grouped pair of data items, we have to consider only from each row, within each row, right? Because we cannot consider the item from here and then another item from the different clusters. Okay, so we consider this in each row, and then also in this group. So what is the number of possible cases? So it is like 1C2, right? Which is 0 because we cannot pick up, choose any 2. And then what about this guy? So it is like 2 and 2 and 3 and 2 and plus 4 and 2, 5 and 2, 5, combination 5 choose 2 and 6 choose 2 and so, right? So in this manner, so from this confusion matrix, if we pick up only from a single cell, and then that is corresponding to having the same label, and then they are grouped into the same cluster. So definitely this number will be much smaller than this, right? So it is having a range from 0 to 1. Okay. So this is the rand index. So that is also a measure of this clustering result clustering quality. Okay, and then this rand index is also extended into ARI. So this is a rand index, and ARI is rand index, but it's adjusted rand index. And in this case, it is making this value of this clustering quality, I mean the range of this clustering quality measure into, so that we can have the zero mean. So in this case, it has some range, but but in this case, so let's think of some easy, one of the easiest case that we can increase this rand index. And suppose we have a freedom to choose the number of different clusters. So number of different clusters. And then in that case, how do we make, or how do we maximize this rand index? And then the most, easiest way would be just trivially to make them into the same cluster, right? So 1 and 4. It's 1, 2, 3, 6, and 15. So making them into one cluster, in that case, we would maximize the rand index, right? So this rand index is having kind of unfair tendencies in a way that it will have a smaller and smaller measure as we have more and more clusters, because we are splitting them into more number of groups. So in this case of a adjusted rand index is kind of compensating, or improving or addressing this kind of issue. This is a how. One, two, three, four, five, six. In this case, what about, what is our clustering result in terms of the number of data items distributed across these clusters? So it's 5, 7, and 9, right? So we consider kind of this situation as kind of default situation, that we just split in total these 20 data items into these 3 groups that has this particular number of data items of 5, 7, and 9. And then we can compute the rand index with no problem. By just considering this and this, right? But what is the expected rand index value when just doing, or when just randomly assigning all these, each of these 20 data items into, randomly again, into any of these clusters, with the number of data items distributed as 5, 7, and 3 into these 3 respective clusters? What will be the rand index value? So I'm actually not clear, honestly. So I cannot fully explain. So if anyone can understand this better, and then please let me know. But this is the adjusted rand index formula. And so let me give a high level kind of an intuition. So let's see. Just okay. So in this case, this is our rand index. I mean the numerator value in our rand index. And what is the Nij? Nij is just a confusion matrix that we have, like a ground truth table. I mean the ground truth versus the predicted one. And then as we saw in the earlier case, so it is like picking up a pair of data items from each cell of 1, 2, 3, and so on, right? So I and J is just an index of maybe ground truth and the predicted cluster layer index, right? And so this was the numerator value that we put in the numerator part. And then what about the denominator part? Okay, so denominator part is as follows. So previously it was just the n choose 2, but in the case of an adjusted one, we just consider its maximum or ideal value over here. And the ideal one is cannot explain. I thought I understood this, but okay. So yeah, if someone can understand, and then yeah, it's in the Wikipedia page, and then from here, why do we have this maximum index on the bottom left? Yeah, maybe, yeah, I don't know how to explain it properly, but yeah, if you guys can, and then yeah, please, yeah, think about it, then yeah, let's try to figure it out together. But anyways, but the main kind of high level kind of idea is that the actual yeah, actual index value is placed on the top left, and then we just subtract it. I mean, we just subtract the expected yeah, expected count that will put the correct ground truth label pairs into the same group. And so this is the random kind of coin flip kind of measure. And then this one is the maximum possible or ideal situation where we yeah, properly clustered all the data item given in yeah, this situation of 1, 2, 3, and 4, 5, 6, and as I mentioned, it's 5, 7, 9. So we just consider or we restrict our situation so that we just clustered our data item into this size of 3 groups of these sizes. So in that case, yeah, that is, yeah, in that case, this is the random kind of case. I mean, random expected number of an index, and so we subtract these common values in both denominator and the numerator. And so in this case, if our clustering measure or our clustering performance was just the same as a random kind of coin flip or a random assignments, and then this index will be exactly, not exactly, but approximately 0. But if we did better than the random kind of assignment, and then this measure will be positive values. And if we did worse than the random assignment, and then it will, yeah, it will even have the negative values as well. Okay, but yeah. Okay, anyways, yeah, that was about the random, yeah, rand index. Yeah. And then, let's see. Yeah, somewhere over here, yeah, somewhere around here, yeah. So, yeah, let me explain another measure called this mean reciprocal rank. So, in the case of this mean reciprocal rank, is as follows. So we consider kind of ranking kind of problem. So suppose we search it for some keywords as maybe Apple, iPhone, or something like that, and then it will retrieve some documents as a relevant document list, and then we can consider the rank of ranked list of these retrieved data items, and then maybe up to 100, considering the total number of data item as 100, and then suppose this guy, suppose we have only like 5 truly relevant data items, or 5 positive labeled data items, and then maybe fortunately the first one was the relevant one, and then the second one was not relevant one, and not relevant, and the relevant one, and so on. Okay, and then the ideal case will be just this one. So all positive ones ranked at the top, and then all negative ones after them, right? So in this case, we just consider the average rank of these relevant data items. So the first data item had the rank of 1 and 2, 3 and 4, right? And then we can consider the average rank of these relevant data items, and then the average rank will be just third rank, right? So it's the first and the second and the third and 5, 6, and then we just take the average, right? But in this case, we can consider this rank as the harmonic mean. So in that case, yeah. So let's consider some non-ideal case as the first and the second, and then the third one was on, like this kind of situation, 1 and 4, and so on. And in that case, suppose we did a really great for the first 4 items, but the last item, the 5th item, was a little bit ambiguous, and then its rank was maybe 90. And then in that case, if we consider this average rank, and then it will be 1, 2, 3. Oh yeah, it's 3, right? Is it 3? It's a 2.5, right? Okay, so so in this case, our rank, average rank, will be this guy, right? But as we can see, this measure is, I mean, this average rank will be better if it's a smaller number, but if we have really a wrong one, or really a low ranked one, and then this integer value will be really high, and thus our average rank will be influenced by this a lot, right? So in this case, this mean reciprocal rank is the harmonic mean of these rank values as this thing. Okay, divided by 5, and then we take the take the inverse of it, and then this way of computing the average rank will be will mitigate the effect of really this poorly ranked ones. Okay, so this is the mean reciprocal rank, but this is just a harmonic mean of the average rank, right? So you can view it or think of it as just an really the on average the true data item was ranked which kind of rank the true data item had, right? So in this case of language generation task, so this is the language generation task in terms of this code level, right? So we can also think of, suppose we have this text sequence of the tokens, and then when computing the softmax scores, and then it will have really long vector, and then we consider the rank of the true data item. So this probably was maybe fourth ranked, and this one was fortunately the top ranked one, and this one was maybe a 30 ranked one, and then we can just compute the mean reciprocal rank of these 3 data items. Okay, so this is how we evaluate the decoded or generated text or code sequences. Okay. And other than that, I don't have much to explain more about this chapter. Is there any questions? Okay, and then so this is the some random topic, but I thought at some point, I wanted to cover this kind of new NLP kind of deep learning model that is quite widely used, and also more importantly, it is increasingly used in many other tasks. I mean, the key idea or concept is being utilized increasingly in many different models. Does anyone know already this transformer or self-attention based models? Self-attention based models. Okay, then let me explain how this model works, and also if I'm wrong, and then if someone is more have a better idea about this, and then please correct me. Okay, then basically this sequence to sequence is based on this LSTM or GRU based model for both encoder and decoder models. And then because encoding is done before the decoding phase begins, and so we can consider this embedding vector or encoding vector is already prepared or is already available. I mean the total embedding vector of the total token in the entire sequence is available after the encoding phase is done. And then let's just think of this convolution based or non-sequence model based this sequence to sequence. But anyways, let's just review briefly the existing LSTM based encoder or sequence to sequence model, and then given this input sentence, so this is just a non-standard representation of the bidirectional LSTM or GRU model. So this is the same sentence except that the reversed order. And so we have one set of encoding and another set of encoding, which is like a bidirectional one, and they are concatenated as a single vector for each token. So we have 4 different tokens in the encoding phase or input sequence, and then in the decoding phase, using this hidden state vector, and then we basically compute the inner product with this and this in the case of a multiplicative attention model, right? So we just multiply or compute the inner product with this vector and this vector, right? And then if that inner product was 3 and this guy is also computed with this guy for its inner product, and then if it was 3 and -1 and 5 and 8, and then we would first convert them into a softmax vector, right? And that softmax vector is used as an attention vector or attention weight, and then we linearly combine them in order to compute the weighted average of these encoding vector, right? And then in the next time step, we have new hidden state vector, and then this one will be plugged into this place. Then this is how this attention-based, it's a sequence-to-sequence model. And then in the case of a convolution-based sequence-to-sequence model, which is a kind of predecessor of this transformer or self-attention-based models, instead is working as follows. So this part, is the LSTM is replaced by the convolution in the encoding phase. So let's just think of this replace the encoding part into this non-sequence-based model by using the convolution thing. And then we consider this a padding. And then so that we can obtain the same number of embedding vector as the number of tokens that we have. And so this is representing the convolution. But we have like 2 sets of convolution thing. So this is called the gated linear unit. This is just a name, but let's see. So this whole part is called the gated linear units, and then a more detailed description is as follows. So we have one set of convolution layer, and then we have another set of convolution layer, but they are just concatenated into a single convolution. So if we have 10 different filters, and then of course for each token we will have 10 dimensional vector, and then we have another set of convolution that has another set of 10 different convolution filters, and then we have a 10-dimensional hidden state vector, and then the row of these 2 vectors are different. So this one is something like kind of an gate in the LSTM, and then this one is like an input gate that is going through the sigmoid transformation. So in that case, we can consider this situation as having the convolution filter, 20 different convolution filters in a single layer, and then the first and the second vector that has the dimension of 10 for each, and then this guy is going through the sigmoid, and then we can do the element-wise inner product with this guy, right? So this part is called the gated linear units, and then this guy is just nothing but the residual connection. That so for this encoding vector is representing this token, and so we would have some embedding vector, and then we will just add it to the output vector for this, and so that's how we achieve this residual connection by adding them together. Okay, so that's this is how we obtain the encoding vector for each token. Okay, So here we avoided this sequential kind of process of doing this LSTM based encoder, and also in terms of the padding, because we need to have the exact same number of encoding vectors for the number of tokens, and so we need a proper padding, right? Okay, and then so far that was the encoding part, and then what about the decoding part? Decoding part, I mean, the role of decoding is to generate the most probable token at a time, right? And so that part is originally done by the LSTM based decoder, but we also replace them by the convolution based non-sequential decoder model. And so yeah. Yeah, initially we given the convolution with the filter size of 3, we start with this P yeah, so PPS. So those two P's are just the padding embedding vector for paddings, and then these are the start of sentence token. Okay, and then the convolution is like in this manner, because we cannot so it's like this kind of thing, right? Because we only use the tokens that was generated up to the current time step. We cannot use some embedding or some information from the future, because we are doing the decoding of generating one token at a time. Okay, so we can also think of this. We can do the convolution thing, and then do the exact same vector for the through this gated linear units. Okay, and then for here, this is some kind of residual connection, but for this part, so we obtained 10-dimensional vector from the convolution layer in the decoder part, and then so using this vector, so this vector works as this vector. Okay, so that is the hidden state vector that will be used as a for the inner product with each of our encoding vector, right? So that way we obtain these which represents the similarity between this token and then each of our encoding vector, like a encoding vector of the input sentence or input sequence, right? So this guy is the same as this guy, okay? And then this arrow is just doing the inner product thing. So these are the inner product, and then after doing the softmax vector, and then we will obtain the linear combination weights, and then using these encoding vector, and then applying the linear combination weights, and then we can compute this weighted average of this encoding vectors, or those vectors that we obtained from the encoder convolution layers. And then okay, and then this guy is actually added with the input token vector. Okay, so that is that is this guy, start of token vector. So you can think of it, so it is really a residual connection thing. Okay, so that way we considered the context vector, which is the weighted average from the encoding vectors, and also the current word embedding or hidden state vector at a certain layer that represents the previous time steps generated token, and then we add them together, and then this is some vector that we obtained that will be directly used to generate the next token. Okay, so once we obtained this vector, and then this vector is going through the linear or fully connected layer, and then do this softmax thing, and to obtain the most probable decoding output or decoding tokens. Okay. Any questions so far? So in the case of this gated linear units, so it's almost the same as the input gate and the LSTM gate thing. Let's see. Okay, so in the case of an LSTM, given by using the previous hidden state vector and the current input vector, we will generate the two sets of vectors, right? And then the overall we are creating or generating the new vector that will be added to our previous cell after going through this forget gate, right? And then the reason why we provide or create the two sets of vector was because so this part is the gate which contains the information that we want to add, but we are going through additional kind of sigmoid gating so that we can kind of selectively remove some information that was generated from this, right? So this is exactly the same in this gated linear unit. So we first compute some information that we want to generate, and then another gating vector that will be multiplied so that we can kind of remove some portion from the generated input data or input signal. So and then here in this non-sequence based model, we actively use this position encoding thing. So in this case, suppose these three words are appearing in this place, and then we will do the convolution on these three words, right? When assuming the filters convolution filter or window size as 3, and then suppose we found these exact phrases composed of these three words or trigrams. We found this trigram over here, and also somewhere in the later part in our sentence. So in that case, they will in this architecture, their embedding vector will be exactly the same, right? Exactly be the same. So in order to kind of distinguish or make a little bit of a variation or some differentiation in terms of their position information, I mean the absolute position information. So overall these three trigram appeared here, and then maybe their kind of semantic meaning may be different. But in the case of an LSTM or sequence-based decoder, because all the previous tokens information is accumulated in the hidden state vector, even if we find the exact same trigrams, I mean their embedding vector, I mean their encoding vector, hidden state vector will be different, right? So the positional encoding works as follows. I think I described it earlier in the previous lecture. So so if we have these this sentence, and then in the case of an embedding vector, for the same word, they will have the same word embedding vector, but they are placed or they appeared in a different position in our sentence, and so so it will have the position index as 1, 2, 3, and 4, 5, right? And then we kind of consider kind of this kind of sinusoidal kind of signal, and then what we would do is what we would do is, so suppose we are 1, 2, 3, 4. We are having 4-dimensional embedding vector, or hidden state vector dimension S4, and then we prepare for these 4 different sinusoidal kind of signals with a different frequency or period value, and then in the case of the first position, we capture these values, okay, and then it will have maybe starting from this guy, it will be like a 0, 0. No, 0 and 1, and 0 and 1. And why is it so? I mean, let's just consider it as dimension 1, 2, 3, 4. Okay, and then this guy has 1, and this guy has 1. This guy has 0 and 1, and this 0 is like from this green line, right? And then in the case of a third position, and then suppose that is 3, and then so we capture those values from these different sinusoidal kind of graphs or functions, and then these 0, 1, 0, 1 vector will become different vector. And so these different vectors, depending on these absolute positions that this each keyword appeared, okay, so that vector will be added to the original word embedding vector. So this is the positional encoding, so that the neural net or the next immediate layer can distinguish the different positions. Okay, even if we see the same same words. 네. 네. 그러니까 여기서 이제 뭐 파인 튜닝이나 아니면 뭐 처음부터 이제 배우게 되는 뭐 그런 벡터를 좀 생각을 해볼 게, 이제 이 워드 임베딩 벡터 자체를 이제 처음부터 학습을 한다 그러면 어쨌건 이게 시퀀스 기반의 모델이 아니면 이제 베리에 대해서의 임베딩 벡터는 하나로 이제 설정이 될 거잖아요. 그러니까 이제 저 베리에 해당하는 저 두 개의 서로 다른 포지션에 있는 저 임베딩 벡터가 뭐 하여튼 따로
인덱스에 대해서 어떤 그 다른 매트릭스를 만드는 그 모델 임베딩 하는 것처럼
네, 오케이. 네. 그것도 따로 학습을 하기도 하고 안 하기도 한다네요. 네. 네. 그래서 이거는 안 하고 그냥 좀 거의 막 생뚱맞게 그냥 난데없이 그냥 가져와서 쓴 거고요. 네, 가져와서 쓴 거고. 근데 어쨌건 그 다음 그 리니어 레이어나 이런 데서 그 저거를 가지고 뭔가 하여튼 다르게만 구별을 해주자라고 하는 의도로 뭐 저렇게 좀 크게 따로 학습을 하지는 않고 쓰는 경우가 좀 뭐 있고요. 뭐 일반적이다라고까지 할 수는 있을지 모르겠지만, 그 다음에 저것도 이제 학습을 좀 할 수가 있는 것 같기도 해요. 그래서 이제 그 경우는 이제 워드 임베딩 매트릭스가 워드별로 4디멘전이면 워드별로 4디멘전 벡터가 쭈르륵 있듯이 이제 포지션별로의 4디멘전 벡터가 있어서 그것도 이제 학습을 하는 거죠. 네. 그러면 하여튼 뭐 임베딩 매트릭스 자체는 맥스 그 포지션에 해당하는 맥스 랭스에 해당하는 그거 바이 4가 되는 거죠. 근데 뭐 하여튼 이렇게 해도 뭐 크게 성능에 지장이 없다고 하네요. Okay, so this those embedding vector representing each position can also be trained from scratch. Okay, but people seem to just use this pre-trained one, pre-trained vector for each position encoding, and also this position encoding is done both on the input sequence or input tokens, and also the output tokens as well. So Okay. So this guy, okay. So this guy is used for, used to decode a particular token here. But when doing this decoding thing, we actually add this position encoding vector as well. Okay. So this position encoding is done in both encoding and the decoding phase as well. Okay, so this is the model overview. So this bottom part is a decoding part, and then padding and the start of sentence token, and then gated linear units, and then we obtain some hidden state vector from the decoding phase, and then we did an encoding vector as well, and then by using this inner product and then doing the softmax vector, and then we obtain one set of a attention vector. Okay, this is the first time steps attention vector, and then this is some added with this guy. So this guy, so this part can be also viewed as some encoding vector, I mean embedding vector, input embedding vector of individual words, and then so these are just moved, or they are just duplicated into the bottom part, and then also we have these three encoding output, right? And then they are added together. So the first one and added to form the first vector, and so it can be viewed as just a residual connection for each different time steps. Okay, and then so these are the main main kind of main encoding vector that will be used to form some context vector based on our attention weight. Okay, so after we obtain some attention weights, and then that attention weights are applied in order to form some context vector that will be used to generate the first token, and then this guy is added to this guy. So this guy worked as some vector that will be used for computing the inner product or attention weight, and also this guy is also given through this skip connection or this residual connection, so that it will be added together with this vector, attention weighted context vector, and then we finally form some hidden state vector that will be directly used to generate or generate our output token at this particular time step. Okay, so this is our softmax vector output, and then this guy will be concatenated over here, and then we added one more time step in our decoding phase, and then now we can do the next time steps convolution thing in our decoding phase, and then we will do the same thing, and then this encoding vector will generate another set of weighting or attention weights. Okay, so this is the process of these decoding in the based on non-sequence based convolution based decoding kind of steps. 네. 네. 리지듀얼 커넥션이요? 그건 뭐 어떤 특별한 이유가 여기 내에서의 어떤 특별한 이유가 있다기보다는 그냥 뭐 리지듀얼 커넥션을 붙이면 잘 되잖아요. 그러니까 이제 뭔가 정보가 한번 트랜스폼이 되면 변환이 되면 오리지널 원래 갖고 있던 정보가 없어지잖아요. 그래서 이제 이쪽을 이제 더해주는 형태로 그래서 우리가 필요한 정보가 뭐 1에서 1.1을 만들기 위해서 여기서 공비를 1.1이라는 잘 좀 이 값을 찾기보다는 하여튼 1에서 나머지 델타인 0.1을 만들어 주는데 이 레이어가 집중을 하자. 약간 이런 거잖아요. 그래서 뭐 그냥 네. 뭐 원래 오리지널 워드의 의미를 뭐 어느 정도 좀 갖고 있을 수 있도록 사실 없어도 뭐 사실 원칙적으로는 말이 안 되는 건 아닌데 그냥 뭐 이렇게 넣으니까 다 성능이 좋아져서 저렇게 아마 하는 게 아닌가. 따로 없나요? 여기 우리 선생님 박천복 선생님이 여기 있어. NLP 전문가. 1시간 전에 나한테 이걸 다 가르쳐주고 내가 지금 강의를 하는데 직접 했으면 좋았을 텐데. 어쩌면 뭐 그러니까 리지디어 커넥션을 이렇게 붙이면 뭐 그냥 성능이 뭐 좀 좋아진다. 뭐 약간 이런 어떤 일반적인 그런 특성에 기반해서 이제 뭐 쓰는 게 아닌가 싶고 물론 괜히 넣은 건 아니겠죠. 굉장히 다양한 세팅에서의 뭔가를 해봤을 텐데 어쨌건 뭐 저렇게 했더니 뭐 좀 성능이 릴라이블하게 잘 나오니까 저 구조를 계속 가져가는 게 아닐까 싶어요. 그러니까 뭐 리지듀얼로 다 점 처리돼 있죠. 여기도 리지듀얼이고 또 여기도 또 리지듀얼 커넥션이 또 있는 거니까. Any other questions? Okay, then so this is about the position encoding. And then in general, even though it's quite minor, but if we add position encoding in the both input and the target tokens, and then the blue score is slightly increased. So it's like an ablation test where we just removed the source position encoding and the target position encoding and both. Okay. And then the performance is better actually than the previous Google neural machine translation or basically attention. I think it's attention based sequence to sequence with the attention model had these kind of performances, and then the performance is increased when using this convolution based encoding and decoding kind of model. And then this transformer thing that we will study in the next hours. Yeah, this one has the better kind of performances. And then also the main advantage, another big advantage of using this non-sequence based encoder-decoder model is that it has it is much faster in terms of a training phase, right? So in this case, so let's figure out or think of where we can parallelize this model. So initially this part and the decoding part were all parallel, and then let's think of the training phase first, and then in the case of training, this kind of LSTM is not parallelized, right? And so if we do the convolution-based encoding, and then of course this part is fully parallelized. But let's look at the decoding phase. In the case of decoding, as we saw in this case, so we need to generate this particular token in order to fill this token kind of, yeah, this particular token, and then this convolution, I mean application of this convolution filter is only done, yeah, this can be only done after this token is actually filled out, right? And then this guy is obtained, and then it will be placed here, and then that's when we can perform the convolution, right? And so it is not parallelized at all, right? So in the case of decoding part, it is not parallelized, but yeah, that's the yeah, that is the testing phase. So in the case of testing phase, it's not parallelized at all, but in the case of training phase, so it is parallelized as well. It is parallelizable because we can first, yeah, we can first fill out all these entire output sentences by using the ground truth one, right? So maybe 네, 나는 학교에 갔다. If this was an encoding sentence, and then I mean input sentence, and if the ground truth decoding or the output sentence was I go to school, and then we just fill out these tokens as a ground truth output, and then it's just doing the kind of predicting the next token, right? And then yeah, we can yeah, fully parallelize as well for the decoding part. I mean in practice, when doing this back propagation, and then yeah, doing the forward prop and the back prop, it can fully be parallelized. Yep. 네.
디코더 파트에서 원래 RNN을 썼다라면 타겟 랭귀지의 어떤 뭐 이전 정보들이 히든 스테이트만 있어서
네.
계속 활용을 할 텐데
네.
컴프 같은 경우에는 최근 이제 필터 그 리스만큼만 보게 되잖아요.
네.
타겟 랭귀지에서는 인코딩은 전부를 다 인코딩하겠지만 그러면 타겟 센텐스가 충분히 길 때 과거에 있었던 그거에 대한 디펜던시를 잃어버리고 그냥 컨텍스트에 디펜던트하게만 아웃이라고 하는 거예요.
지금 요 컴브 베이스요.
네.
그러니까 이게 결국은 n그램 기반인 거잖아요. 필터 사이즈가 n이다 그러면 결국 n개의 토큰만 보고 하여튼 정보를 뽑겠다는 건데, 그런 측면에서 맞아요. 저 앞쪽에 있는 걸 못 보죠. 못 보는데 이제 이게 저기 저쪽 이제 셀프 어텐션 쪽으로 가면 이게 좀 이렇게 모두가 모두를 보게 되는 좀 네, 그런 구조로 바뀌면서 이제 그런 롱텀 디펜던시가 좀 꽤 이제 꽤는 아니고 거기서 이제 거의 완벽하게 좀 약간 잡히게 되는. 그러니까 하여튼 컴프는 딱 그 말 그대로 n그램 그 이외에는, 그러니까 이 아웃풋을 요거 하나를 생성할 때는 네, 여기서 보인 그 이전에 만든 그 단어 딱 n개 프리비어스 단어 이외에 내가 볼 수 있는 정보가 아마 없죠. 네. 디코딩 단에서는 내가 윈도우 3이다 그러면 네 번째 전에 내가 무슨 단어 생성했는지는 전혀 영향을 못 주는데, 네, 컴프 기반에서는 그렇죠. 그 셀프 어텐션 기반은 안 그렇죠?
네, 이게 그렇게 해서 이렇게 저기가 좀 쉽게 하기 위해서
네.
컨볼루션을 하나만 쌓았는데 실제 모델에서는 컨볼루션 레이어 여러 개를 좀 쌓아서 좀 필드를 좀 증가시키는 방향으로 해서 좀 더 많은 페이지를 보도록 하게 하는 것 같아요. 그래서 이제 그런 페이지 정보를 계속 전달해 주기 위해서 디테일 커넥션이 존재하는 거라고 좀 약간 생각할 수도 있을 것 같아요.
네. 그러니까 이거를 한 레이어로만 하는 게 아니라 컴보를 이렇게 계속 쌓게 되면 우리가 뭐 알다시피 이게 리셉티브 필드가 점점 커지잖아요. 네, 아마 그래서 뭔가 더 이제 필터 사이즈보다 더 위쪽으로 올라가면 좀 많이 보게 되는 게 아닌가. Okay, so yeah, because of the main kind of limitation of this convnet convolution property, so yeah, we cannot, we can only see the previous tokens within a certain length of time steps, but if we add more and more conv layers, and then the receptive field gets larger and larger, and thus we can incorporate much longer kind of dependencies into our decoding phase. So this is a convolution-based sequence-to-sequence model. Any other questions? I think it's yeah, although this exact architecture is not much used because it was, I think it's, we now have a much better model of this transformer or yeah, self-attention based model. Yeah, but yeah, the base model is almost the same as this guy. So it will be useful to understand this quite well. Any other questions? Okay, so this is the attention kind of visualization. Uh, uh, so at each decoding time step, yeah, we can yeah visualize this entire matrix. But this matrix, I mean, each row is filled out one by one at each decoding time step, right? And then what if we actually, yeah, what if we do the multi-layer convolution in the decoding phase? In the decoding phase. 그게 저 깃허브의 그 그림인가요? 깃허브 링크가 있었나요? 여기? 없나요? 손시대요. 이 중에 볼까요? 첫 번째 거, 두 번째 거. 뒤에 거요? 뒤에 거 같네. 응? 이거 맞나? 네. 그 오피셜 거기 깃허브에 있죠? Okay, so I wanted to show this figure. Yeah, so we first go through the encoding thing by using the convolution on the input sequence or input tokens. And then, so this is the version of using multi-layer convnet for the decoding phase. Okay, decoding phase. So, yeah, so it's a zero padding and start token. And then I don't know what this means, but suppose we have this convnet as filter as having this kind of shape, and then yeah, for each output, and then we just compute the product-based or multiplication-based attention weights, and then these are attention weights, and then these are kind of context vector, and then this guy is used to compute these attention weights, and also after obtaining the context vector, and then this guy will be added as a kind of through the residual connection, and then so basically this guy or this guy is those kind of residual those context vector added with this encoding vector from the component, right? And then these are attention. I mean these are the new or the one step higher level of encoding vector of our decoding kind of tokens, right? And then using these vectors as the new embedding vector or new representation for each of our tokens, we can do the same thing. So using that, using this guy, and then using it as a kind of inner product based or multiplication based attention weights, and then obtaining context vector and so on. Okay. So at each layer of our convnet in our decoding phase, we do that kind of attention based context vector and incorporating it into our hidden state representation for each decoding token. Okay, and then we can now understand these figures. So I think it's a decoding phase, convolution layer index of 7 and 8 and so on. And then at each layer, we can compute these decoding, attention weights. And then in some layer it's not clear, but in some layer attention weights are kind of clear. And so yeah, when stacking the 3 layers of convolutions, and then yeah, the first and the third one looks quite reasonable, and then the second one is kind of yeah, vague. But anyways, we can visualize these attention weight layer wise at different layers. Any questions so far? Okay, then let's take a break and then continue at 3:35.
지지난주에 예비고를 가가지고 저희가 출석 그것 때문에 뭐 저희 따로 제출을 서로 가져오면 돼요.
이메일만 좀 보내줄래요? 그러면?
아, 네.
이메일.
네.
저번에 나 예비기 가서
네, 이메일 좀 알려줄래요?
이거
아, 이거 알았어요.
조교님이 뽑아오러 왔어요.
아, 조교가?
네네. 조교한테 물어봤을 뿐인데
알았어요.
뽑아달라고 하더라고요.
I finished
The SVS and the extract.
SBS and actually there is some open source code.
Right. That's open slide, right? No? Is it a different one?
Open source code available in the GitHub to extract to remove the label.
What's the project name? It's open slide still, right? No?
And anonymized slide something like this.
I see. Oh, I see. Ah, there is a specific.
Just one Python file, Python code.
So that removes the label.
Yes.
Okay, great.
Only remove the label.
So maybe if you are, yeah, if you have time in the evening, I just give you the files so that you can remove the label. But at the same time, we need to maintain. I mean, we need to basically scramble those IDs so that we can de-identify them. So yeah, we cannot just remove them. I mean, and also after you remove it, were you able to extract out the uncompressed image? Not just the SVS file. You just
remove them.
Okay. Yep. Then yeah, please let me know if you can extract out the uncompressed image file so that we can just import it in the Python or
We also prepare the Windows PC.
Oh yeah, okay, that's great. Yeah, that's great. Thanks.
펌프 시퀀스가
네.
아까 그 학생이 질문한 게 앵그램이니까
네.
그 과거 히든 스테이트의 정보를 못 담냐고 질문을 하셨잖아요.
네.
근데 이게
네.
어차피 만약에 하나의 토큰씩 아웃풋으로 내뱉고 계속 이 인코드 디코드 작업이 계속 같이 가는 거면은
네.
결국 이 어텐션 부분에 의해서 컨볼루션이긴 하지만
네.
과거 부분을 가지고 온다라고 해석할 수
네.
있는 거 아니에요?
그럴 수 있죠. 네. 그러니까 인풋은 우리가 다 보긴 다 봐요.
네.
그러니까 여기서 이제 전 시퀀스의 전 토큰들에서 이제 우리가 필요한 정보를 뽑아오는 게 매 타임스텝마다 이루어지는 거니까.
그러면은 여기에 있는 컴보는 훨씬 더 그러니까 모든 그
그렇죠. 어텐션이랑
퍼포스에 대해서 다
네. 그러니까 요거에서 인코딩을 할 때는 일단은 단어를 이렇게 세 개씩 보는 거는 맞고, 네. 그러니까 인코딩은 그러니까 로컬하게 해요.
네.
전체 컨텍스트를 보지는 못하고 다만 이제 아까 얘기했던 것처럼 포지셔널 인코딩을 통해서 이게 전체 중에서 어디쯤에 등장한 거다라는 거에 대한 정보는 그냥 그 정도만 알고 있고.
네.
근데 이제 디코딩을 할 때는 중요한 게 이제 쭉 이렇게 가면 우리가 LSTM 기반으로 하면 이제 쭉 뒤쪽에서 뭐 단어들을 생성하면 각각 단어들을 생성할 때 그 전에 이제 내가 뭘 생성했는지에 대한 전체 기억을 내가 다 갖고 있다라고 할 수가 있잖아요.
네.
근데 여기서는 그러지는 못하는 거죠. 그러니까 내가 요 세 개를 생성했고 그 다음 걸 생성할 때는 내가 이 네 번째 전에 그러니까 3이라는 걸 쓸 때는 얘를 내가 뭘 생성했는지 내가 완벽하게 까먹은 거죠. 네, 그 차이가 좀 여기서는 좀 있는 거죠.
그리고 그 이해가 안 가는 게
네.
그 테스팅 타임에서는
네.
모델이 패럴라이즈드 하지 않는데
네.
트레이닝에서는 그렇다라고 설명하신 게 이해가 안 돼요.
그러니까 여기서 이게 다 지금 이게 다 있으니까
네.
인풋이 다 있으니까 이제 그 바로 다음 단어만 이제 우리가 생성해주는 태스크를 하면
네.
이게 기본적으로 컴브 베이스니까 이게 다 패러렐라이즈가 가능한 거잖아요. 그러니까 쭉쭉 올릴 수가 있잖아요. 그러니까 이 시퀀스에서 컴브로 배치로 싹 한 방에 벡터라이즈드 된 걸 뽑으면 바로 이 시퀀스에서 바로 다음 단어, 그러니까 각각의 단어에서 바로 다음 단어로서 생성할 그 각 타임 스텝에서의 토큰들을 한 방에 쭉 뽑을 수가 있는 거잖아요. 그러니까 컴브에서도 우리가 돌아가면서 이걸 하잖아요. 이 돌아가면서 하는 거를 그 저기 시퀀셜하게 할 필요가 없이 다 패러렐라이즈가 가능한 거니까 여기서도 이제 트레이닝 단에서는 패러렐라이즈가 가능하다는 거죠. 쭉쭉 올라가면 거기서 각각 그라운드 트루스 아웃풋 다 걸어서 쭉 이렇게 백프랍을 하면 이게 다 동시에 지금 될 수가 있는 거죠.
모델이 패럴라이즈 됐다는 것 자체가 어떤
자체가 이제 여기서 계산할 때 그러니까 지금 이 시퀀스에서 지금 여기까지 했을 때 요거 또 여기까지 했을 때 요거 단어를 생성하는 거 요거가 지금 동시에 생성이 가능하냐 아니면 이제 여기서는 이제 이거를 가지고 와서 여기 쓴다 그러면 동시에 생성을 못하죠. 하나씩 해야 되는데 지금 얘가 예를 들면 i를 생성을 했는데 실제 여기에 들어가는 답은 u예요. 그럼 여기를 일단 답으로 다 채워놓고 하면 이게 패러렐라이즈가 가능한 거죠. 내가 맞았든 틀렸든. 근데 이제 디코딩을 할 때는 이제 이쪽 뭐 만든 거에서 이걸 다시 일로 갖고 와서 이제 쓰잖아요. 그러니까 이런 어떤 저기 테스팅 단에서의 이런 식으로의 디코딩 단에서는 이게 패러렐라이즈가 안 되는 거예요.
패럴라이즈를 해야 되는 뭐 이유가 있는 거예요?
이유는 이게 학습이 빨라지니까. 이게 컴브를 이렇게 하면은 이게 다 배치를 이렇게 GPU에 다 한꺼번에 들어가서 이게 한 방에 되거든요. 네.
두 가지 여쭤보는데 여기 보면은 그 똑같이 보이는 좀 뭔가 다르게 표시된
그러니까
것
이게
같아서
좀 이상한 것 같아요. 예, 맞아요. 이게 좀 다른 것 같아요. 그러니까 이게
그림으로는 똑같아요.
네, 그러니까 이게 그러니까 이쪽이 이거 나도 잘 모르겠어요. 그러니까 이게 왜 두 개가 있는지 잘 모르겠어요. 이 그림이.
그리고 이제 약간 애매한 부분인데
네.
두 개가 있잖아요.
네.
컨버전 되고 나서의 그 상태랑
네.
그다음에 뭐 액티베이트 된 상태를 이 부분 두 개로 네모가 두 개로 되어 있는데
그러니까
액티베이트 전과 후를 표시한 거.
아니에요. 20디멘전을 생성해서 처음 10디멘전은 그냥으로 쓰고 두 번째 10디멘전은 이제 그 시그모이드를 통과시켜 갖고 그걸 이제 그 엘리먼트 와이즈 멀티플리케이션 해준다는 거죠. 우리가 이제 LSTM에서도 이제 IFOG를 한 방에 네 세트 벡터를 한 방에 다 생성한 다음에 이제 맨 위에 거는 뭐 예를 들면 뭐 시그모이드 그다음에 하나는 타네이치 하나는 시그모이드 해갖고 네 개의 벡터들을 이렇게 나누어 갖고 각각의 역할별로 따로따로 쓰잖아요. 네, 여기서도 그런 식이야. 총 이제 20벡터를 만들어서 그러니까 컴브는 그냥 하나의 컴브가 있다라고 보면 되고 그래서 이제 컴브 필터가 20개가 있어서 20디멘전을 생성했으면 이 중에 반은 우리가 시그모이드를 통과시켜서 얘를 필터링 혹은 게이팅을 해주는 데 쓰이고
이게 약간 컴버라는 게 필터가 돌면서 그 리니어 프로덕트로 뽑아낸 다음에 액티베이트까지 되는 게 컴버라고 하나요?
액티베이트, 네, 그러니까 여기서는
리니어 썸만 생각.
첨보 학생, 그 저기 게이티드 리니어 유닛에서 그 시그모이드로 빼는 거 말고 그 밸류들을 갖고 있는 거는 그냥 리니어 한 다음에 따로 타네이치나 뭐 이런 거 안 걸죠. 렐로나. 그냥 그건 리니어 아웃풋 쓰는 거죠. 네. 알겠습니다. 네. 그래서 그거는 우리가 갖고 있는 하여튼 유의미한 밸류들을 갖고 있는 벡터라고 생각을 하고요.
네. 이 표시는 그 포객.
네, 맞아요. 포객 게이트랑 거의 동일한 거예요.
동일한
이게
거죠.
요거예요.
이렇게 이전 스테이트랑 현재 스테이트 느낌으로 같이 결합하는 것처럼.
네, 근데 이제 좀 더 정확하게는 이 부분이 아까 내가 얘기했던 딱 이 부분이랑 거의 동일한 거예요. 이 부분.
X.
네, 그러니까 여기에 타네이치를 걸어서 우리가
얼마
유의미한 시그널을 만드는데 이 타겟치가 그냥 없는 버전을 쓴다고 생각하면 돼요.
여기가
여기서
리니어한 부분 바로
네, 리니어한 거를 이제 두 세트 벡터를 뽑아서 한 세트는 시그모이드의 게이트. Okay, let's continue. Okay, then let's study. Yeah, it's an advanced architecture called transformer, and yeah. So the official paper name was "Attention is all you need." Okay, so this is the official paper title, and it was published in yeah, last year's NIPS. So yeah, but when it was when it was open or made available in the archive, so yeah, people got really excited about it. And then yeah, so let's study how this works. Okay. So here, so suppose we have the input tokens and their embedding vectors, and then using this position encoding, yeah, it's yeah. In the case of sigmoid, it's like represented as this, but in the case of position encoding, yeah, we represent this kind of sinusoidal kind of thing. But yeah, it can be any other kind of position encoding, kind of, function output. But yeah, so yeah, we added the position encoding into each of our embedding vectors, and then let's look at this part first. And yeah, this one is called the self-attention module, which works quite well in many different applications. And so self-attention is basically attention within themselves. So yeah, typically in the case of an attention, we consider kind of a decoding phase over time steps, and each time step in our decoding phase, we kind of compute the attention vectors that will be assigned to the encoding I mean, encoding vector of the input sequence, right? So the main entity will be the decoding, decoding thing or decoding time step, and then the ingredient or the those entities that will be assigned for the encoding. I mean, attention weight will be the input sequence tokens, right? But in the case of self attention, so we are given these set of these three vectors, and then we just consider their basically attention between within themselves. So in other words, this guy, for this guy as a kind of a decoding kind of a hidden state vector, and then we can compute its attention over the same set of the encoding vector, and then we can just compute this guy times this guy. I mean, in terms of the inner product, and then another one and another one, and that way we can compute the encoding, I mean, attention weights, and then also another set of attention weights and another set of attention weights. So which means just a pairwise kind of similarity kind of matrix, right? Where each row is containing kind of a softmax vector that will sum up to 1, right? So this is a main kind of idea of the self-attention, okay, self-attention. And then given these three input sequence vectors, and then suppose when this guy was inner product with the self, itself, and this guy, and then suppose that attention vector was 0.7, 0.2, 0.1. Okay, so in this case, so we just compute the average, I mean weighted average by using these attention weights, and then we obtain some new context vector, and then this context vector can be used for the new encoding vector after the next layer that represents the first time steps token. And then for this guy, it will be computed the inner product. I mean, for the inner product with itself, and then this guy, and then attention weight will be changed, and then we can compute the context vector, and then we can obtain this context vector for the second time step by using the self attention, right? So in this case, if we optionally use the residual connection, so yes, do you see? We see this residual connection. So again, this one is from. I'm not sure. 저자도 똑같아요? 저자가 어때요? 그 전에 컨브 S2S랑 이거랑. 저자는 어때요? 완전 달라요? 둘 다 페어인데 저자는 달라고? 그런 거요? 이건 구글인가? 이거 구글 브레인. 네, 그렇죠. Okay, so I was confused, but I think this transformer is motivated or inspired by the conv S2S, I think. 맞나요?
여기 나오기 전에 제가 알기로는 뱅티오 그룹에서 그 센텐스 레프레젠테이션을 셀프 어텐션 기반으로 한 게 있어서 거기서
그래요? 그럼 그 논문은 이 컨브 S2S랑은 어떤 관계가 있어요? 관계가 없어요?
그것까지 제가 말씀드렸습니다.
그래요. 네. Yeah, so I don't know their exact relationship, but from my limited experiences of just quickly checking out the previous paper of conv S2S or sequence to sequence and this attention, I mean transformer model, they share a lot in common. So okay, so one commonality is this kind of residual connection. So we can optionally just put this skip connection or residual connection so that this guy will be added to this guy, right? And then in this case, so if we do this self-attention in this manner, and then there is a kind of one kind of limitation, so that always the inner product with itself. So in the case of this, it will also compute the inner product with itself, and then in principle, the inner product with the same two vectors will have the maximum value in terms of their similarity, right? So these values will have naturally this value will have the largest one, right? But if we consider this kind of a residual connection, and then if we just think of, so basically this kind of self-attention is, intuitively you can think of or understand it as the process of bringing or delivering some relevant information from, so it's like, it's handling or it addresses the long-term dependency by just bringing the relevant information in the very far time steps directly into the current time step. Okay, so if this word was strongly related to this word, and then if the time step gap between these two input words are quite far, and then in terms of an LSTM or sequence-based encoding, and then it has to go through many kind of layer, many time steps in order to properly deliver or convey the information from here to here, right? So this kind of a long-term dependency is kind of addressed by just considering all the pairwise relations, and then being able to bring those information from any kind of time steps into any time steps as well, right? So that way we consider all the possible pairwise relationship, and then so we kind of we kind of think of this kind of mesh kind of, or fully connected kind of structures in our neuron. Okay, so that's main kind of idea of being able to handle the long-term dependency in this self-attention based architecture. Okay, and I personally think that this kind of idea is quite effective in many other, including this in this model, and also in many other applications. Okay, and then back to this. So if we use these types of attention weights that has the pattern of having the largest attention weights on itself, and then if we just think of this residual connection, and then we just need to deliver some additional information that is necessary or that is meaningful from other entities, because that will be the same one will be just added together, right? And so sometimes, or in many cases, we don't actually need to bring the information from itself, right? So one way would be to just make into zero, I mean by excluding it, but this is not actually what we do. So what we do is to extend our attention mechanism by using some kind of query and key and value thing. So this query and key and value thing is quite important. Important one. So values are okay. So in this, even in this original sequence-to-sequence model, so this guy will be the common vector. That will be used to compute the inner product with each of these vectors, right? So this common vector can be viewed as key. Okay, so it is basically a key, and then using that key, I mean, you can imagine some kind of a hash table. Okay, so we have some key that we can find some proper address, right? And then we will basically find out which particular address that we are trying to find, right? And then so this is like a 0x1001 or something like that, and then this address is 0x100 and 0x1000 1001 and 1002 1003. So I'm thinking of this kind of really physical memory kind of structure that has the address as 1,000. It's a hex number, but that's just view it as a decimal number. Decimal number is 1000 and 1001, 1002, and 1003 are those address values. Okay, so those addresses, yeah, if you think of the hash table, and that address can be viewed as a kind of particular string, right? So that string is like, yeah, so if you, so that is called a dictionary, right? In the Python thing, right? So this address is like a particular string, like cat, or maybe a dog, and things like that. Okay, and then in this address, we can think of is kind of value or content in that memory address, right? So that way, those values that are not necessarily just number, but they are just address values, but also they can be viewed as keys, right? And keys are indicating, yeah, really the keys that that will help to find the particular memory address. Okay, and then we have actual memory contents, right? So those are called values. Okay, and then this one is actually it's called a query. So if our query is cat, and then what we are doing is to find out the particular keys that has this same query thing, right? And once this guy was actually cat, and then this memory content is what we want to extract out, right? So I'm just trying to explain this from the perspective of a kind of a hash table or kind of a memory and their address and their contents and so on, right? Okay, so far so good, right? And then, so in the neural net, they are all done in a kind of soft, kind of a, inner product and maybe softmax and sigmoid and things like that, right? So in order to match or in order to find out which particular address that we are looking for by using this query keyword, and then we are actually doing the inner product with the query and each of our key parts. So suppose we have key 1, key 2, key 3, and the associated value 1, value 2, and value 3, and then we can just compute the inner product between Q and K1 and Q and K2 and Q and K3. Okay, and then typically if we find this particular one, and then that weight will be 0, 1, 0, and then that will be like used as a linear combination weights of these values, right? And then if it is a 0, 1, 0, 1, 0, and then it's just having an effect of just picking up V2, right? But it is just all soft. So if it is a 0.1, 0.7, and 0.2, and then it means that our key is not having an exact match, right? Exact match. But with the first key, it has a matching score of 0.1, 0.7, and 0.2. And then by using these, and then we can just linearly combine these associated values so that we obtain one single value. Okay. So this is how we kind of retrieve some relevant information by using this key query thing, by matching this query with the key. Okay. So back to this example. These keys that will be used to compute these linear combination weights, and also these values are actually the same thing in the previous attention model, right? In the original attention ones, these keys and the values can be considered as the same one, right? And then our query vector is this hidden state vector, right? Okay, having that in mind, so here, what is key and what is query and key and value in this case? So in the first time step, the query was that same vector, and then what was the key? So key was this one and this one and this one, and the value was also the values were also these three vectors. So far so good, right? But the reason why we obtain high value or high matching score between this query and K1 and K2, K3 is because this Q is actually, or this query is actually the same as K1, or this query, I mean the key vector, I mean the first key vector, right? So yeah, in order to kind of generalize this, we actually extend this previous attention model so that, okay, so we have a 3 ingredient vectors, and then we consider its own linear transformation, maybe WQ, so that we can generate or convert these vectors into a query vector, okay, when they were used as really the query vector, okay. And then also by using the same set of an input vector, we can also consider or think of another kind of linear transformation that will generate its key values and also the value thing, okay. So that way we can prepare for 3 different versions of like vectors, yeah, that will work as a query, key, and value respectively. So far so good, right? And then sometimes, yeah, sometimes we actually omit this part. So the main intent is to prepare for 3 different sets of vectors in terms of their roles of the query key value. But yeah, in order to do that, we consider the 3 different linear transformation. But yeah, even if we just remove one of them, and still we can still have the 3 different sets of linear transformation. I mean the 3 different sets of a vector for query key value, and then typically these ones are used as a query ones, right? The original ones are used for query one, but yeah, I think in this transformer model, we have all these 3 different linear transformation, but in some other simpler model, sometimes we don't use the this part, so we just use the original vector as just a query vector, okay. And then the rest of the stories are the same, I mean, from the perspective of an attention. And then in that case, since we since we change it into a different set of vectors, so we can avoid this kind of problem of having the highways on the same identical ones, right? So we can have like whatever necessary attention ways, even for these self-attention based kind of approaches. Okay. And then sometimes, yeah. So this is a main idea of the self-attention, and yeah, this is this attention part, because this is self-attention. And then what about these multi-head? Okay, so let me just describe these 3 arrows. So these 3 arrows are representing like a query key value, and then yeah, after doing so, yeah, we understood this attention part. But what about this multi-head attention? Multi-head attention. So multi-head attention is so maybe it's like this. So I study math at night, for example. Okay, so in this case, so we want to augment some information for this time step about I. So in that case, we can kind of consider like adding some additional information about this I. So I is just an I, but this sentence is representing the activity that I did, and also like the time information as well. So we can augment some information in terms of the particular activity that I did, which is about like a studying, and then also another types of an information that we want to add in terms of this time point that this activity was done, right? So in that sense, our kind of key value and yeah, this kind of self-attention mechanism is to augment some meaningful information to that kind of particular current time steps information. But such an augmentation of an information can be kind of in different forms. So sometimes we want to add or we want to augment the information from the perspective of the particular type of an activities, but some other types of information from in terms of the time steps and the location and things like that, right? So such a different aspects of an information that we want to augment can be implemented or developed by using multiple sets of these different attention mechanisms. So typically, in this case, we even though we prepare for 3 different sets of these WQ, WK, WV, that will produce only one particular linear combination of the those information. But in order to add, maybe augment some time point information, we may need different ways of an attention, different ways of computing attention ways, and then also the value can also be different. So because the value should mainly contain the information about the time point, not just the other information. So we can prepare for multiple sets of these attention kind of not mechanism, but these are linear transformation weight matrices. So multiple sets of these linear transformation matrices, and so that is called the multi-head attention, because we are achieving these attention-based information augmentation in many different aspects or from the many different ways. So that is called the multi-head attention. Okay, so so this is the batch processing that is represented by the simple matrix multiplication, but I'm gonna just skip this part. Let's see. Okay, and then so we just concatenate all these vectors that were extracted from many different aspects, right? So the first vector, that is the augmented information about the activity, and then maybe time points and so on. So we just simply concatenate all of them in order to form the first time steps embedding vector for this guy. Okay, so that's how we kind of increase the dimensionality of each time steps hidden state vector. So there is this concat part, and then this head I is having these W, I, Q, W, I, K, W, I, V. And then typically Q, K, V are, Q, K, V, which are the input vector, is this guy, the same vector that is given as an input to the 3 different rows. 이건 뭐야? W. W5는 뭐야? 아, 이 위로 가는 거? 그럼 여기까지 리니어, 그러니까 리니어 레이까지 포함하는 거예요? 저 셀프 어텐션 레이어? 멀티 헤드 어텐션이? 뭐 제가 한번 디멘전 좀 줄여주나 보네요. 줄이는 거죠? 이 컨캣을 해갖고 뭔가 디멘전이 늘어났을 것 같은데 이걸 좀 줄여주는 게 아니에요?
헤드를 만약에 8개로 하게 되면
네.
각각의 뒤에서 어텐션 예를 들어서 전체 원래 썼던 모델의 디멘션 510이면 8 나누기는 30이잖아요. 64가 되잖아요. 각각의 헤드 어텐션에 나오는 밸류가 64 해가지고 전체가 컨캣을 하면 원래 있었던 그 히든 디멘션하고 똑같게 만드는.
그럼 여기서는 하는 게 뭐예요? 이 리니어가? 지금 그걸 설명한 거예요?
그거는 컨캣을 해주는 리니어가 약간 좀 컨캣 때 정보
한 번 더 좀 변환을 해준다. 네, 바로바로 공부하면서 가르치려니 나도 힘들긴 하는데. 그래서 뭐 이게 So in terms of the number of dimensions, suppose we had a maybe 100 dimensions as an encoding vectors, and then suppose in the previous attention mechanism, if we compute the context vector, and then the context vector will also be a 100-dimensional vector, because that will be just the weighted average of these 100-dimensional vector, right? But if we use these maybe 5 different heads or 5 different aspects that we want to kind of augment the information about, then yeah, we are basically obtaining 5 different sets of the attention weighted context vector, each of which are just a 100-dimensional vector, and thus dimension will be 500. But if we reduce the dimensionality for this value part in terms of the size of WV, and then if WV was first changing these vectors into like 20 dimensions, okay, and then the attention context vector or attention weighted vector of these 20-dimensional vector, which are our value vector, and that value vector will have has much smaller dimensions of the compared to the original vector, and then in that case, even after we concatenate them, then we can maintain the original dimensionality, okay, instead of just increasing the dimensionality in proportion to the number of heads, right? Okay, and then the next one of this linear transformation, is additional kind of a layer that we add. Okay, and then here in this transformer, they use this scaled dot product attention. So what I mean by that is, so it's basically, I mean, still, even if we just extend this attention mechanism into like having key, value, and query things, but still it's still a multiplicative, multiplication-based attention model in a way, so that this query vector will be used for the inner product with each of our key vectors, right? So let's see. So this is a query vector, and this is the key vector, and then we will perform the inner product, and then suppose our key and the query vector, I mean their dimension should match, of course, and then if we had a 100-dimensional vector inner product, and then so this one is typically going through the softmax layer, which is like, this single inner product value will be transformed by this this kind of transformation using an exponential function. But if we think of this value, and then this one is basically the sum of 100 different numbers. So this guy times this, and this guy times this, and so on. And then when viewing them as just a random variable, which means that each of these values that will form this summation of 100 different values. So suppose this one is like kind of IID and maybe normal, following the normal distribution with the zero mean, and then maybe univariance and so on. And then the summation of them, and then their variance will be 100, right? That is obvious one, right? So in that case, because simply because this is the sum of 100 different values, and thus their variance or their absolute value could be a little large, or that could be a little bit far from the origin of 0. And then of course the softmax, this guy is like, so if it is a large value, then it can really explode really easily, right? So the resulting attention kind of model, like, so for example, 1, 3, 2, and maybe 100, 300, 200. And then this guy's softmax vector is like maybe 10% and 70% and 20%. Although it's just a hypothetical number, not an exact number, but in this case, it will be really like 0 and 0, almost like 99.99 and 0.05 and 0.05 and things like that. So it will lead to this kind of extreme attention weight in the case of a high variance values. So in order to mitigate this kind of process, we just after doing this summation from this inner product computation, we just divide it by the square root of the dimensions. Okay, so that way, even if we just sum the 100 values, and then if we just divide it by this square root of number of dimensions, and then it can mitigate this kind of explosion of our variance. But I'm not sure why it is dividing it by dk instead of square root of dk instead of just a dk. I'm not sure exactly, but that is kind of playing a role of mitigating this high variance value. So it will give a little bit mild kind of attention weight like this, 0.1, 0.7, and 0.2. Any questions so far? Okay, so back to this overview of our model. So we covered up to this point, and then now we have a residual connection, and that is represented by this add, and then this norm is actually the normalization layer. Okay, so given our input vector, and then this guy, and then this is representing a residual connection, and then this normalization is done by this layer normalization, and then suppose we have these three vectors, and then from some self-attention and then skip connection through some skip connection, suppose we obtain the some hidden state vector in the next layer, and then the layer normalization is doing the normalization of those four numbers. So if it was 1, 2, -3, and 2, and then we just first make it as zero norm, zero mean, and the unit variance. Okay, so we just simply subtract the mean and then properly scale them so that the variance or the standard deviation to be 1. And then we also, similar to this batch normalization, we just do some scaling and then the shifting. Okay, so this guy is the standard, unit norm, zero mean, and the unit variance, and then we just properly scale and then shift them, and then these two are the trainable parameters. Okay, so the trainable parameters. 근데 이거 공통된 파라미터예요. 그러면 이거 GI랑 BI랑 그래요? 근데 I가 왜 붙었죠 그러면? I가 디멘전 인덱스? 그렇죠. 네, 디멘전 인덱스. 오케이. 근데 그러면 이것끼리는 얘네들을 내서 노멀라이제이션을 하고 우리가 여기다가 스케일링 및 쉬프팅은 각 디멘전별로 따로따로 해줘요? 그래요? 이것도 좀 트리키하네요. 그러니까 뭔가 배치놈에서는 지금 이거를 노멀라이즈하고 여기를 같은 값의 평균으로 빼고 나누고 하되 여기다가 트레이너블한 파라미터로서 쉬프팅 및 스케일링을 하는 거는 또 같은 값을 쓰는데 이거는 지금 그러니까 각 디멘전별로는 그 스케일링 및 쉬프팅이 다르죠. 이거는 지금 이 내에서 노멀라이제이션 평균을 0, 분산을 1로 하고 또 여기 내에서 또 디멘전별로 스케일링 및 쉬프팅을 따로따로 해준다. 네. Okay, so once we normalize them within this four-dimensional vectors or four numbers basically, and then we scale and shift with the different parameter values which are trainable ones for each separate dimensions. Okay, So that is the layer normalization, and then that is this norm thing. Okay, and then that hidden state vector will also be going through the this feed-forward or fully connected layer, and then suppose each of these vectors are going through the layer normalization, and then suppose we obtained the output after doing this layer normalization, and then for each of these vectors, we just go through some fully connected layer. But these fully connected layer for each time steps are actually the same. So they share the parameters. So that is called this feed forward one. So okay, and then once we transform them into another set of vectors, and then we just go through the skip connection or residual connection, and that is called this add, and then also we perform this layer normalization as well. Okay, and then also this this guy, this feed forward is also described as a one by one conv thing. So if we just form these as a single matrix, and then we have these 3 time steps, and then so suppose if we do the conv with the window size as 2, and then this will incorporate these 2 vectors at a time, and these 2, and at these 2 as well in the next time step. But in the case of one by one kind of conv, and then it will just use only this information to form the first time steps activation map, and then the same shared parameter will be applied in order to change or transform into another vector for the next time steps, and so on. So that way it can be viewed as a one by one conv, but it's not really a 2D data, so it's a one-dimensional conv, or I mean the convolution with the time step, I mean the convolution with the window size of 1. Okay, so we can view that feed forward one as this convolution layer. Okay, so this is the encoding part. This part. So that is corresponding to, and like this part. Okay. 네. 그러니까 밸류가 이제 서로 다른 버전이, 그러니까 밸류를 뽑는, 그러니까 원래 히든 스테이트 팩터가 100디멘전이었으면 그거에 웨이트가 어떻게 걸리든 뭐 100디멘전 3개가 있으면 다 리니어 웨이티드 에버리지는 100디멘전 벡터를 만들잖아요. 근데 이게 어텐션 웨이트를 주는 방법이나 이 100디멘전 벡터에 대한 표현형 자체, 그러니까 이게 밸류로서 작용을 해서 얘네들의 리니어 콤비네이션이 되는 거잖아요. 그러니까 이 밸류들이 한 5세트가 있어서 이제 우리가 5개 서로 다른 방식으로 어텐션 웨이티드 에버리지 벡터를 뽑겠다라고 하면 이 100디멘전al 벡터가 사이즈가 그대로 밸류가 그냥 100디멘전al 벡터였다 그러면 이게 그냥 5세트가 있으니까 그 5세트를 다 콘캣을 하게 되면 500디멘전이 되는 거잖아요. 그럼 뭐 이렇게 멀티 헤드 개수만큼 이제 헤드 개수 곱하기 밸류 벡터의 디멘전이 이제 총 디멘전이 되겠죠. 그렇죠? 그렇죠. 너무 커지니까도 그렇고, 또 기본적으로 이제 리지듀얼 커넥션은 이제 디멘전이 안 맞으면은 이게 안 되니까. 그래서 맞춰줘야 되니까. 네. 그래서 뭔가 이거를 500디멘전을 먼저 만들어 놓고 그 다음에 리니어 레이어를 써갖고 100디멘전으로 줄인 다음에 그 다음에 뭐 이제 리지듀얼 커넥션을 통해서 애드를 할 수도 있을 거고, 네. 아니면 뭐 밸류 자체를 좀 작게 만드는 것도 방법일 수 있겠죠. 그러니까 예를 들면 아까 뭐 얘기했던 것처럼 멀티헤드라는 게 어떤 특정한 애스펙트에서의 정보를 기준으로 그 정보를 이제 어그멘트를 해주겠다라는 얘기니까, 이제 그게 뭐 어떤 우리의 그 히든 스테이트 벡터는 뭐 굉장히 여러 종류의 정보들을 다 갖고 있는데, 거기서 뭐 장소만 뽑겠다, 뭐 어떤 뭐 아까 액티비티 타임만 뽑겠다, 그러면 이제 훨씬 더 적은 수의 디멘전으로 표현이 될 수도 있겠죠. 그러니까 뭐 밸류들을 디멘전 적게 쓰는 것도 또 말이 되겠죠. Okay, then the next part is a decoding part. Okay, then in the previous model, the decoding was like sequentially, I mean one at a time, right? One at a time. And so you can also think of that same process in the decoding kind of process of the transformer model. So that is called this shifted right, I think, right? So it is also starting with this pad, maybe start of the sentence token, and those three are the initial embedding vector that we start with. I mean, assuming that we have some kind of conv thing in the case of previous conv S to S, but this is basically a self-attention based model. Okay, self-attention based model, and so in this situation, so we just consider that as the entire sequence that we currently have. Okay, so in that case, yeah, we do this multi-head attention that we studied in this part. Okay, so this part is exactly the same. Okay, exactly the same. And then let's just forget about this masked part. Okay, for now. Okay, and then given these three embedding or encoding vectors, and then we do the transformation to the key value, query key value, and then do this self-attention thing, and then we will obtain some output vector for each time step, right? Okay, so that way, so in general, like, so suppose we want to generate this word school, and then up to the current time step, so we obtained these three words that we already generated in the decoding phase, and then in that case we can just apply the self-attention layer, and then we obtain these three vectors, right, after doing this self-attention. Okay, so in that case we just have to bring the encoding vector information. So up to this point, we just apply the self-attention only within the decoding decoding tokens and their encoding vectors, right? But these input sequence and their information was not incorporated yet, right? So how these are incorporated into decoding phase is based on the attention and their attention weighted context vector, right? So that part is done in this phase. Okay, so you can think of the lower part of doing the multi-head attention within the decoded output so far is that we just incorporate some information by just addressing some long-term dependency in the decoded sequence so far. Okay, and then this is the main kind of attention kind of mechanism that we previously used in many other models. Okay, so let's look at that. Okay, so this part was done used as a query and key and value. So that's why we have these three different common kind of arrows. But in this case, there are two arrows coming from here, and then another arrow from here, right? So among these three, so which were value key query. Okay, so these using these three encoding vectors from the input sequence, we provide value and key, right? And then for here, these three vectors, will work as the query vector, right? But typically, previously we used the query vector by only using the last hidden state vector. But in this case, we are using all these three vectors as the multiple query vectors that we use. Okay, and then suppose we have 4 different time steps in the input sequence, and then using each of our embedding vector as a query vector, and then our kind of pairwise similarity matrix or kind of attention thing is like 3 by 4, right? So when using this as a first query, and then for the input sequence, 4 different input sequence vectors, and then we can obtain some attention weights, right? Attention weights, and then using these attention weights, and then we just linearly combine them, right? And then that will further be concatenated or kind of representing the hidden state vector, I mean the new representation corresponding to the first time step in the decoding phase. And then the second, using this as a new attention vector, and then second, embedding encoding vector, and so on. Okay, so that is still done. That is still done by this multi-head attention, and then we use the ski connection and then the layer normalization by just adding them into the same vector. And so we still have the embedding vectors. I mean the same number of decoding tokens, okay, as our set of encoding vectors. Okay, by using these 3, so similar to this, we apply some conv layer with the window size of 1, and then do some ski connection and the normalization, and then still we obtain these 3. Set the vector of these 3, a set of these 3 vectors. And then do some further linear transformation on them in order to obtain one single. 아닌데. 다음에 어떻게 되는 거예요? 프로젝션? 근데 이게 벡터 길이가 다르잖아요. 네. 그러니까 여기까지는 지금 3개의 벡터가 나왔잖아요. 그렇죠? 그러니까 디코딩이 igo2가 아니라 igo2 더까지 나왔으면 4개 벡터가 나왔을 거예요. 이 배리어 길이가 벡터 개수가 다른 경우에 이걸 어떻게 하나로 합쳐요? 근데 여기서 이제 나와야 되는 아웃풋 프로바빌리티는 그러니까 벡터 하나가 나와야 되잖아요. 왜냐면 단어 하나를 뽑아야 되니까 지금. 네. 그러니까 지금 벡터는 3개고 우리는 한 세트의 벡터를 얻어야 되잖아요. 여기까지는 맞죠 지금. 그러니까 요 단계까지는 디코딩 지금 갖고 있는 우리가 시퀀스 조 개수만큼이 나오는 거죠. 벡터가. 그죠? 저 3개를 어떻게 한 벡터로 합쳐요? 길이가 다를 수 있잖아요. 그러니까 지금 여기가 디멘전이 100이고 이게 지금 3이잖아요. 이때도 우리의 그 보캐뷸러리 사이즈가 뭐 1000이다. 그럼 1000 디멘전 벡터를 얻어야 되고 100이고 5일 때에도 역시 1000 디멘전 벡터를 얻어야 되잖아요. 왜냐면 단어를 디코딩을 하나씩 해야 되니까. 지금.
1000짜리 매트리스 곱하게 되면 5 곱하기 1000이
그러니까 5 곱하기 1000이면 그러니까 5개짜리 벡터가 나왔잖아요. 5개 벡터가 나온 거죠. 1000디멘전짜리가. 근데 우린 1000디멘전 벡터 하나 뽑아야 되잖아요.
퀄리티
네, 그러니까 여기 쿼리티 밸류가
계속 하나로 나중에 합치는
하나로 저 애드랑 놈은 뭔가 이 타임 스택 간에 합치는 게 아니라 타임 스택 별로 그냥 스킵 커넥션 혹은 리지드 커넥션을 추가한 거잖아요. 그러니까 여기는 이제 이게 그러면은 마지막 것만 갖고 가요? 이 쿼리를?
퀄리를 해가지고 밸류 값을 얻어내게 되면
그러니까 이 쿼리가 하나예요? 아니면은 여러 개예요?
퀄리는
각각 하나? 각각 네. 아니, 그러니까 지금 iGoTo일 때는 이 세 개가 나오잖아요. 이게 다 쿼리로 다 쓰이는 거예요? 아니면 마지막 거 다 쓰여요? 그러면은 결국은 iGoTo에 해당하는 이쪽, 그러니까 이 빨간색 여기까지가 이 iGoTo 세 개가 각각 갖고 있는 100디멘전al 임베딩 벡터가 나오는 거잖아요. 100디멘전al 임베딩 벡터 세 개가 나오잖아요. 네? 아니, 그 feed forward라는 게 이제 input 디멘전이 이제 픽스가 되어야지 되는 거잖아요. 그러니까 저기서 1000디멘전al 벡터 하나를 뽑아야지 되는 거죠.
만약에 배치 프로세싱 하면 저 빨간 스파트를 하게 되면 배치 곱하기 센텐스 랭스 곱하기 히든 디멘션이 나오는 거잖아요. 그렇게 되면 그냥 저희가 마지막 배치 곱하기 그 랭스를 하나에 그냥 쭉 배치를 보고 그냥 히든 디멘션만 저희가 피드 코드에 붙여주게 되게 되면 걔를 이제 저희가 원화서 넣는
그러니까 이게 누적의 문제냐 아니면 마지막 거 하나만 쓰느냐의 문제인 것 같은데.
그 저희가 테스팅할 때 마지막 하나씩 뽑을
네, 그러니까 테스팅이나 뭐 트레이닝은 단지 그거를 그냥 배치화한 것일 뿐이라고 본다면, 그러니까 하나씩 하는 거를 이해를 하면 그냥 그거에 대한 배치 버전을 이해를 하는 거는 어렵지 않잖아요. 그러니까 이거 하나씩의 버전을 생각을 한다면,
테스트한다면 그 스타트 토큰 저희가 스타트 토큰에 대해서
그러니까 요 지금 뭐 iGoTo 뭐 여기다 스타트 토큰까지 있었다. 그러면
iGoTo까지 제작했는데 그 스토어를 만들고 싶으면 그 저희가 툴에 나온 것만 사용해서
그러니까 얘만 쿼리로 쓰는 거예요?
네,
얘만 쿼리로?
얘만 이제 나중에 리니어 레이어 붙여서
그러면 이게 지금 이거를 얻는 게 아니라 지금 요 단어 하나를 생성할 때는 요거 하나만 쓰는 거네요. 그러니까 요 정확하게 요거죠. 그러니까 쿼리를 얘로만 쓰는 거예요. 배치 프로세싱이 아닌 지금 버전에서는.
네, 배치 프로세싱이 아니에요. 근데 만약에 학습할 때 그냥 저게 나오는 결과가 하나씩 왼쪽으로 옮겨졌다라고 생각하고 나오는
그럼 단어 하나만 생성할 때는 여기에 들어가는 쿼리는 어떻게 보면은 뭐 가장 지금 마지막 타임 스텝에서 디코딩을 지금 했을 때 가장 마지막 단계에서의 타임 스텝에 해당하는 그 벡터만 쿼리 벡터로 들어가는 거군요. 그럼 뭐 내가 좀 넘겨짚고 설명을 좀 잘못했네요. 그러니까 하나를 지금 생성할 때는 지금 여기서 멀티헤드 어텐션 이 아래쪽까지는 여기까지 왔고 여기서 이 두 개는 버리는 거네요. 뭐 버린다기보다는 걔는 뭐 이전에 어떤 단어를 생성하는 데 쓰이긴 했을 수 있겠지만 어쨌건 여기서 이제 지금 넥스트 토큰이라는 이 스쿨을 생성할 때는 얘 하나 싱글 벡터를 쿼리로 써서, 그죠? 그럼 얘를 쿼리로 써서 이쪽에서 넘어온 키에 대해서 다 해갖고, 네, 얘에 대해서의 얘에 대한 이제 어텐션 웨이티드 된 벡터를 가지고 와서 그거 하나만 해갖고 그 벡터를 가지고 이제 리니어 레이어 및 소프트맥스를 거쳐서 어떤 단어 하나를 얻게 된다.
인코더의 인풋이 원래 인코더의 그 인풋 시퀀스 전체가 다 인풋 정도가 되고.
그렇죠. 그거는 항상 그렇죠. 원래 어텐션 모델에서도.
항상 픽스 바뀌는 값이 아니니까.
네.
엔코더에서는 인풋이 여지껏 생성된 워드까지의 시퀀스가 이전에 뽑아낸 텍스트까지의 시퀀스가 인풋이.
그렇죠.
근데 이게 학습할 때는 저희가 다 주어져 있으니까
네.
결국에 학습할 때는 시퀀스가 한 번 한 번 쭉 들어가면서 빨라지지.
네. 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 그게 이제 여기서 이야기하는 요 마스크드 부분이거든요. So, yeah, I think yeah, we consider the kind of decoding phase of generating one token at a time, and then this last hidden, the hidden state vector at the last time step will be used as our single query vector, yeah, to form this attention weighted, input hidden state vector, and then that will go through the rest of the layer to produce one single one token in the next time step. But what about this masked multi-head attention? So this masking thing is that masking thing is related to the fact that we provided the ground truth tokens all in the beginning. So this is the related to this kind of thing. So in this case, so we are given this input sequence of and then we have these three vectors, and then suppose okay, so this is our target output that is already available as the ground truth. Okay, and then up to this point, what is the prediction predicted word? That should be to and the and so, just like the language model thing, right? And so here in the training phase, so we given all these tokens are available from the ground truth, and then we perform this multi-head attention thing, which is our self-attention layer. And then the self-attention thing, if we imagine some self-attention, I mean, we are just talking about this part, okay? And then the self-attention layer would be just the same as the self-attention layer for the input token sequences, okay? So in this case, so we have a residual connection like this, and then like some kind of attention vector, right? But in this case, our attention, so if we imagine some kind of attention weights of 0.1, 0.2, 0.3, 0.4, and 0, and so on, and then in this case, these attention weights assigned to the later tokens in the time step cannot be used in the training phase because we didn't generate these attention weights yet, right? But still, we just compute this kind of a 1, 2, 3, 4, 5 by 5 matrix. So this guy is the attention weight that is assigned, that is for the first time step, and then this guy will be 0.1, 0.2, 0.3, and 0.4, and 0, right? So in this case, we cannot use these attentions, right? So we cannot bring those encoding vectors into the previous time step, right? So we first compute all these pairwise similarity matrix so that each row is sum up to 1, okay? And in that case, after then, we just okay, so we just leave these values and those values as 0. So we just set them as 0 because we cannot assign these attention weights on them, right? Does it make sense? Okay, and then yeah, those vectors will only involve those context vector that involves only up to the previous or the current time steps information. Okay, so this kind of like a zigzag pattern kind of a thing is called this masked multi-head attention. But I think that is used for the this type of a batch processing only done in the training phase. But in the case of testing phase, we need to perform this kind of decoding phase one by one. 네. And then the performance in terms of the accuracy of the blue score is slightly better than not slightly, but it's better than the original sequence to sequence with the attention model, and then also it's much better, better than the convolution based sequence to sequence model. And then this one is training cost in terms of the number of flops involved in the computation, and then most of these sequence based models compared to those models, these transformer one seem to involve much smaller computations. 네, 그래서 이게 몇 배 빨라진다 그랬죠? 경험에 네? 3배? 3배쯤 빨라진대요, 학습이. 테스트단에선 이게 뭐 느려질 일은 특별히 없죠. 시퀀스 투 시퀀스 모델보다 느려질 일 있나요? 네. 디코딩은 네. 더 드릴 수 있겠죠. 네. 그러니까 아까처럼 뭔가 하면 뭔가 한 단어 한 단어를 생성하는 과정에서 뭔가 중복된 계산이 또 있을 수도 있고 해서 네, 하여튼 그래서 좀 오히려 테스트단에서는 그냥 시퀀스 투 시퀀스 모델보다 이게 시퀀스를 쓰지 않은 모델이라고 하는데도 이제 더 느릴 수도 있다. 뭐 약간 그게 또 제 생각엔 좀 중요한. 근데 뭐 인코딩은 하여튼 뭐 패러렐하게 이제 빨리 될 수가 있는데 이제 디코딩 단은 좀 아까 얘기했던 것처럼 여전히 이제 하나씩 해야 되니까 거기서 뭔가 좀 중복된 계산이라든가 뭐 이런저런 좀 네. Okay, so this is the recent paper that Chonbok introduced, and this was published in iClear this year, maybe less than a month ago, but it was available in the archive much earlier than that. But so this the main idea of this paper is to be able to parallelize the decoding phase as well. So as we saw, the decoding phase is just inevitably just a sequential. So this is a sequential kind of decoding kind of process. So in the case of an encoding one, and then I think this one is based based on the this one is a transformer thing. So up to this point, so we will use those based on the self-attention only applied to the up to the current time steps, and then we will bring these attention-weighted encoding vectors to generate these hidden state vectors. Okay, so that is the sequential process of in the decoding process, decoding phase. But in their models, so the main idea of this approach, I mean, the main idea is not originally proposed in this paper. So similar idea was already proposed in the previous or another paper. But yeah, I also vaguely know about this model, but let me just briefly explain how it works. So these are the input sequence, input tokens, and then those numbers are called some kind of fertility. 뭐죠? 이름이? 아까 뭐 있었는데. 네. fertility score or fertility number or something. Yeah. So the meaning of it is, that so when translating this input into output sentence, sometimes one word is translated into multiple words, but some words may not be translated at all. I mean, in terms of the explicit mapping between input and output tokens, right? So in that case, maybe there are can be just interpreted into just 있다. 그러니까 뭐 이 단어가 한 단어로 만들 수 있고, 혹은 네, some one word may be translated into multiple words in the target language, and so those numbers are just the number of target tokens that will be translated from each token in the input sequence. Okay, so this one should be translated into 2 words, 0 words, and 0 word, 2 words, and 1 word. Okay? And so in the decoding phase, we are not doing this one by one kind of decoding process or style. It is just doing the word level translation from these input words into the output. So if we just duplicate, so some words maybe there twice, and also there's a million twice, and the ways just the once. Okay, and then we have to also figure out. Yeah, we also have to figure out the proper order. So if it was like the subject and maybe verb, and then maybe subject should be placed first in the case of having to reverse the grammatical order, right? And then this entire network will also figure out the proper order as well, not just the number of these words that will be used to be translated into the target words. Okay, and then once we obtain the reordered or properly ordered word sequences, and then the rest of the process will be just directly translating each of these input words into the target word, and it's one by one. Right? So that's in that case, that way we can just do this parallel or kind of a batch processing or batch operation for the decoding phase. Any questions? Okay. 시간이 지났네요. Okay, so I hope it helped. Yeah, for understanding this transformer thing and the self-attention, and maybe we may look at other papers as well, but in the next classes. But the self-attention was recently applied to GAN for the pure image generation task. So there is a paper called the self-attention GAN, recently published, and so that is also using this kind of self-attention thing between different patches in our images, right? So, okay, so that's it for today, and thank you very much, and I'll also announce the other lectures to watch until the next class. Okay, thank you. 네. 수고했어요.